This is a quick video over Kirchhoff's current law. And the idea of Kirchhoff's current law is very simple. It says the change in the charge, Q, with respect to time is simply equal to 0. So if we look at node 1, we say this is node 1, then whatever comes in must leave. So I1 minus 30 milliamps minus 10 milliamps must equal 0. Again, that's assuming there's no buildup of charge, that the charge is equal to 0. So we can simply solve for I1. I1 is simply equal to 40 milliamps. So we know what I1 is, 40 milliamps. Let's find out what I2, I3, and I4 are. So I2, well, we'll look at node 2. So we assume the charge at node 2 with respect to time is equal to 0. So that means I2, whatever's coming in to this charge, so we add up all the currents, or node, not charge. So we just add up all the currents. So I1's leaving, so that's a negative 40 milliamps. And I3, we don't know what I3 is. So we'll just put minus I3. So we can't solve for this because we have two unknowns and only one equation, so we'll move on. We'll go to this one. So we'll assume the charge buildup, or the change in charge at node 3 with respect to time is equal to 0 again. Change colors real quick. Oops. There we go. So we'll just add up all the currents going into node 1. So we have I4 minus, plus 30 milliamps. We have this coming in, minus I2, and then minus 20 milliamps. So we have two unknowns and only one equation, so we'll just move on to the next node. So this will be node 4. So the change in the charge at node 4, I'll change colors. Q4 with respect to time is simply equal to 0. Again, that's because of Kirchhoff's current law. We're assuming that's true. So we have 10 milliamps coming in. We have I4 leaving, and supposedly we have this one leaving. So we have 10 milliamps minus I4 minus a negative 15 milliamps. So that's just 15 milliamps plus 15 milliamps. So then I4, we can actually solve for I4. I4 is equal to 25 milliamps. So we know what I4 is, 25 milliamps. And lastly, let's go to this one. So go with green, this one. Node 5. Again, we assume the charge buildup at node 5 with respect to time is equal to 0. So we have I3 coming in plus 20 milliamps, and we also have an additional 15 milliamps coming in this way. So that's actually minus 15 milliamps. So now if we solve for the charge of I3 is just simply equal to a negative 20 milliamps plus that 15 milliamps, because we just moved this over here and distributed the negative charge, or the negative sign. So we have I3 equal to a negative 5 milliamps. Now what is this really saying, this negative 15 milliamps right here? That's really just saying that the current's actually going this way, and this is actually positive, a positive 15 milliamps. So if we just flip the sign and say this is going that way, we can just say that's a negative 20 milliamps. So you can flip the arrow and then just add a negative if you flip the arrow. So just because the arrow is pointing one way does not mean that the current's actually flowing that way. So I3, which is equal to a negative 5 milliamps, the current is actually flowing this way, a positive 5 milliamps going that way. But since the arrow is drawn the other way, it's a negative 5 milliamps. So finally, let's go back to node 2. We know what I1 is, and we know what I3 is. So therefore, I2 is just the negative 40 milliamps minus the current I3. So what we get is I2 is equal to, we just move I2 over, distribute the negative sign, we get 40 milliamps plus I3, which is a negative 5 milliamps. 5 milliamps. So what we get is 35 milliamps, right? Because we have 5 milliamps coming in this way, and we have 40 going out that way. So that means we must have 35 coming in this way. So 35 milliamps. I think we have everything solved. We have I1 solved for, I2 solved for, I3 solved for, and I4 solved for. So that is how you use Kirchhoff's current law to solve a very simple circuit.